Hello everyone. Thanks for making time to come here and getting to know about this new amendment. Yeah. So just for me to know how, at what level I need to explain things, can you show hands on how people who are familiar with that 11 protocol? Okay, good. So this part has two sections. The first section is on high efficiency 11AX, which has been under development for a couple of years now, and it's more mature. The draft is ready. It's going through the comment resolution. And the second part is the wake-up radio, which is a new development. And the way I will do, I explain about AX, like 3 questions, and then wake-up radio, and at the end we will have time for more questions. So about IEEE 2.11, as you know, this .11 defines the standard for wireless LAN networks. And it started back in 1989 when some people decided to do a product authorization request. The PAR is a document that people submit to IEEE standard rules, and then they approve it based on what is the scope of it, what is the purpose of the project. And once it is approved, then in .11 there will be a study group and task group to develop the standard. So the first revision of a standard was in 1997, and I think you're all familiar with this trend of Wi-Fi. It started with, actually before 11B standard, there was a Wi-Fi that was used mostly in warehouses to scan objects and send it to local computer network there. And then it found out that it's useful. It can be used as a wireless communication between devices, and 11B was developed, which had the data rate of 1 to 11 megabits per second. It's a single carrier direct the spectrum, and then it was useful. So it became popular, and then the 11A and G, which were OFDM, they were developed. Now, around the 11A G time frame was then this wireless LAN NIC cards become popular, and Apple and Intel, first Apple and then Intel, they put it in their laptops. And once Intel put it in the laptops, it was actually the first project I worked on in Intel. The Intel advertised a lot. They spent money, they put it on airports and hotels, and it became really, took off in the market. And at that time, people used it for web browsing and doing Google type of stuff. And then the demand increased. It was useful to use it for, applications such as YouTube, Netflix, watching movie, and then the highest throughput one, 11N came. 11N was using the MIMO technology. From 11N to 11AC, so always the demand was to go higher throughput, and eventually in 11AD, it's a 60 gigahertz band, that is much shorter range, but much higher throughput. It's 11AD is like for sync and go application. You can download the movie very quickly and then go to the airport. I think to go to plane, there are some airports that apparently have this kiosk that you can download movie quickly to do AD. But then the IoT and wearables came to the market, and there was demand to address the low throughput but longer range and low power. So then AH was developed, which was completely backwards. It was longer range for sensor networks. Let's say if in campus you want to cover a bunch of sensors in the smart grid, and or in a campus you want to put some low-rate connectivity available. So AX was developed. And then, so things seem to be okay. Still, I think you all experience, you are in a hotel room, you connect to Wi-Fi, but it's really, really slow. It's really, really slow. Or you're in airport, if you're lucky, you get connected, but the connection is very bad. So what was the reason was the overall network throughput. So the system was not designed really for having every person, now carries a cell phone and a laptop. Kids have cell phones. They all on the Wi-Fi. It's just amazing. Like my daughter's friend come to our house, and the first question they ask, "What's your password?" They came to talk to each other and play with each other, but they are all on their cell phone and connecting to Wi-Fi. So it was that how can we improve the user throughput, the way that user see it in a dense network. So that is why AX was developed. And AX is at the same band in the 2.4 gigahertz or 5 gigahertz band, same as 11N and 11AC. It uses the same OFDM and MIMO technology, but it developed new techniques to improve the throughput that we will see. And then after AX, we have all the IoT and wearable devices still that they need low power, and the problem with Wi-Fi going to these IoT and wearables is really the power consumption. All Wi-Fi devices we use have rechargeable batteries, like cell phones, right? We have to recharge it. The wearables that we have like or the IoT devices such as like a motion sensor, they have like a AAA battery or a small battery, non-rechargeable, and they last a year. Such a thing is impossible with Wi-Fi today. So how can we address the power consumption of the Wi-Fi? So the idea of low power backup receiver was introduced, that we will see. It's a new sort of angle to Wi-Fi. So I think I talked already about this on the need for high efficiency, and it's also that in like apartment buildings, each apartment has its own access point, and it's really dense, right? So the access points have intelligence to pick the channel, carefully to avoid interference, but anyway, the channels are limited, the spectrum is limited. And besides that, we wanted to have outdoor operation. So Wi-Fi, we have cafes and like a Starbucks, they provide the hottest spots and malls, they're outdoor. So how the Wi-Fi was again traditionally developed for indoor application, how can we go to the outdoor? So this is really we want to see how the user experience improves. So there are some examples of use cases for 11AX that motivated actually development of 11AX. I'm going to quickly go over them. So here is one is the wireless office, which like the teleconferencing and video conferencing is application which is really high throughput demand. And the remote diagnosis and treatment are another example. The other example I already mentioned is this residential apartment buildings. And note that here the access points are unmanaged, unlike the enterprise that, like for teleconferencing in a like a TI building or campuses, they are managed networks, so access points can be connected through the backhaul. But here it's completely unmanaged. The other example is in exhibition halls that are a lot of advertising going on. People get some information, they want to send a report out. These are like really hundreds of people uploading, downloading a lot of data at the same time. Another example is in public transportation. Now the planes have Wi-Fi, buses have Wi-Fi, but they still, or subways, but it still is not seamless. So it's not like if you get out of the one station in subway and want to get to another train, you get disconnected. So this can be a managed network that you continuously have connectivity. So another example is, of course, wearable devices and augmented reality and video analytics, or these fancy gadgets, Google camera, Google glasses, and other. If they have equipped with Wi-Fi, you can do more things than just the Bluetooth, because Wi-Fi has higher throughput and has the IP connectivity. The other example is in a stadium. Stadiums also have very good managed network, and it's just beamforming to cover all the areas, but still it's hugely dense, right? So we want to address them. So this was the scope of the project. As I mentioned, it's in 2.4 gigahertz and 5 gigahertz. And the goal is to improve the user throughput. And the product authorization request document, define that they want to improve 4 times better user experience compared to 11 AC. And also to improve the power efficiency of Wi-Fi and auto deployment. So these three were the goals of AX. So now, how did the MIMO was already there, OFDM was already there. So how did we develop this more efficient techniques? Was to, the number one was we had OFDM in Wi-Fi, but not OFDMA. So the whole band was assigned to one user. But now OFDMA is introduced to Wi-Fi, which is like if you have 256 subcarriers to orthogonal subcarriers to create this OFDM, you divide them between users, so each user gets a portion of that 256 points. So what's good about that is that there are a lot of short packets. And for each short packet transmission, the control packets, management packets are short. But still, because Wi-Fi is a listen before talk system, for each short packet, the device has to go through the contention of the media and access the media, transmit to the embedder, interframe spacing to be considered between each frame. So it is like for each short transmission, you have a lot of overhead in the air, and if you can multiplex them together, it is much more efficient in terms of use of a spectrum and time. So the OFDMA was defined for both uplink and downlink. And then multi-user MIMO also has been added, the uplink multi-user MIMO. The downlink multi-user MIMO was defined in 11AC, which access point usually have more antennas, so they can do, in 11AC there are like access point has 4 antennas, to each station has 2 antennas, so they can do simultaneously two stream multi-user MIMO for each of these stations. But it was introduced in the uplink, and we will see that in uplink has its own challenges, so that was the new effort. And the other thing is the special reuse. Again, Wi-Fi is listen before talk, and in fact it is very conservative. So the threshold, detection threshold is at -82 dBm. So that today's Wi-Fi, if they detect another Wi-Fi device, which is at low as 82dBm, they won't transmit. They think that media is busy, they hold back, do the back-off contention and wait till the media is free. But reality is, if there is a signal, weak signal here at minus 82 dBm and I'm close to my access point, I can transmit. Some sort of collision can be handled. So it is very conservative design. So this special reuse and changes of clear channel assessment has been defined to allow more concurrent transmission of Wi-Fi. And then the other thing was, of course, with the advances in technology, we can have 1024 QAM modulation. In AC, we had up to 256 QAM. So 1024 QAM is an optional modulation scheme added to 11AC. It has improved we'll see how to support the outdoor operation. And of course, with the OSDMA, and if the users have a smaller bandwidth of allocation, they can focus their transmit cover, they can improve the PSP limit there to gain from the power imbalance. So we'll see a thing about this too. So now what's the challenge with uplink and downlink OSDMA in uplink? It's very important that these signals come to the access point synchronized. Now how is this transmission from different users become synchronized? Was a challenge because again the Wi-Fi is this and this before talk, it's a random access to the media. So if each user is randomly accessing the channel, how can we guarantee that they are synchronized? So what AX has defined is the concept of sending a trigger frame. So it's like prior to AX, Wi-Fi has been always on a synchronized system. So whoever sends the channel, if channel is free, they transmit. So there is no central synchronization going on. But in AX, access point has the control over the media. It sends the channel, it transmits a trigger frame, and by trigger frame, it defines who is going to transmit next. And that way, the sort of scheduling happens. But still, Wi-Fi has to be backward compatible. And the legacy devices all are going through this random access of the channel and contention. So access point, the AX access point, will be contending for the media along with other legacy devices. And once it gets it, it transmits the trigger frame to get a transmit opportunity to reserve the channel for some time. And the Wi-Fi, as you know, is always to be backward compatible and coexist with legacy devices. They include legacy preamble. So again, in AX, it has a legacy preamble. Legacy preamble is detected and decoded by all legacy devices. Within the legacy preamble, there is a signal field which has the length of the packet. Now, access point, 11AX access point, let's say if it wants to reserve the media for 3 milliseconds, in the legacy signal field, in the length field of legacy signal field, puts, I'm going to transmit a packet for 3 milliseconds, just a spoof of all the legacy devices. And then after this legacy portion of the preamble, then comes the actual preamble for the AX devices. Now, the AX devices will be able to decode their own preamble, and they will detect that, okay, this is a trigger frame, it's for a station ABC to transmit next, but all this information from a legacy device is like, some Wi-Fi packets that it's encrypted, they cannot decode it. All they know is that through that length field, they know that the media is busy for 3 milliseconds, so they know that they should not use the media. So this is the main thing. Now another benefit of this trigger frame is that when the station receives the trigger frame, through the preamble, they know what's their timing offset, what is their frequency offset. So when they transmit uplink after trigger frame is done, the station ABC know that it's their turn to transmit uplink. They adjust their frequency offset and timing offset based on what they receive from the prior transmission. So this adjustment of time and frequency offset needs to stay valid. So it has to be within really short time. The response has to go back. And Wi-Fi has always a very restricted time constraint as opposed to like LTE or WiMAX. Those are synchronized systems. They define frames and subframes, and then the next subframe in another 1 millisecond or 10 milliseconds is time to transmit. So it's, the station have enough time to buffer, to decode, to even run the HRQ algorithms. But in Wi-Fi, it's not the case. The Wi-Fi transmits the packet for 16 microseconds later, the acknowledgement has to be sent. And if acknowledgement is received, okay, the packet transmission was successful. If acknowledgement has not been received, the retry happens. There is no nudge or something. So it's really time constrained. Same thing here. In trigger frame, 16 microseconds after trigger frame, the station transmits back, like a station ABC in OFDMA fashion or multi-user MIMO fashion, they transmit back. This 16 microseconds, while it is a very hard constraint for the implementation of the devices to turn around and, decode the packet and figure out what they need to transmit next. But the good thing is that it allows them to stay synchronized. So if the trigger frame, they synchronize they correct their timing offset and frequency offset, it stays valid. 16 microseconds later, it stays synchronized, it receives the access point. It's still at the access point needs to do the per user phase tracking, for example, to make sure that, handles any residual error. But that should be okay because access point is a powerful, expensive device. I think I covered all of this. On power imbalance. So usually, access point, for example, Wi-Fi access point transmit at 18 dBm or 22 dBm. And Wi-Fi is an unlicensed band that transmit power. The regulatory domain has hard limits on the max transmit power. So it's like 2.4 gigahertz and 30 something dBm in US, much higher than other regulatory domains. But usually access point transmits 23 dBm. But this is like our cell phone transmits at this 23 dBm. It drains their battery very soon. So cell phones usually use 14 dBm for transmission. So now this is the power imbalance. Access point also has more antenna, has higher antenna gain. So this becomes like a link budget issue as well. So the way that we could address it in AX was to use the subchannelization gain, which is this access point transmits 23 dBm in 80 megahertz of bandwidth, but on the uplink transmission, we assign only an OFDM May sub-allocation of like 10 megahertz. So this way, the total transmit power is focused on 10 megahertz and gain the subchannelization gain. So that was another advantage of going through the OFDMA. And this is a tone plan of OFDMA. So unlike usual, OFDMA systems that you have seen, they define a resource unit and then a multiple of resource unit is used. In Wi-Fi, is not that's not the case. The smallest unit is 26 tone, and I think I have a slide on number of subcarriers, but I should have had it earlier. So the 20 megahertz bandwidth is divided to 256 tone, or 256 FFT. And 26 is like equivalent to almost 2 megahertz. So this is the smallest allocation of 26. In theory, you can have 37 users being multiplexed together in OSDMA fashion to transmit uplink or downlink with 26 tone allocation. And 26 tone allocation comes from 11AH development. So it's very important for Wi-Fi manufacturers that these devices are cheap. They want to reduce the implementation cost, and they like to reuse as much as possible. So 26 tone allocation was defined for AH for 1 megahertz bandwidth of AH. They thought that, okay, we use that. Again, reuse it so that hardware can be reused. Then another step above 26 is 52, which happens to be the twice of 26 also, but it's not because it is twice of the 26 tone. It is because the 50 tone 2 allocation was used in 11A and 11G, so they picked it from that architecture and that implementation. Then above 52, the step is 106, and 106 is not a multiple of 52, but they could use 104, but they use 106. The 106 happens to be a better number for the existing interleaver block. So Wi-Fi has a convolutional code, and the convolutional code there is an interleaver. Interleaver is block interleaver, and 106 works better with the existing dimension of that interleaver. Then another one above that is 242, which is coming from 11AC tone allocation. And that is like 242 tone is equivalent to like 20 megahertz of bandwidth. So you can have 4 20 megahertz users, then 484 and eventually 996. So Wi-Fi has 20 megahertz, 40 megahertz, 80 megahertz, and 160 megahertz of bandwidth 80 and 160 are in 5 gigahertz band, and 20 and 40 are in 2.4 gigahertz. 20 and 40 is also in 5 gigahertz band. So usually 5 gigahertz band has higher bandwidth, is used for higher throughput devices, and 2.4 gigahertz is used more for devices that need a better range, because the frequency is lower, it has a better range. So now MU-MIMO, the multi-user MIMO was, of course, a way to exploit the spatial coordination, the spatial domain for multiplexing. And the good thing about MIMO, I think you're all familiar with this, is that the bandwidth, we cannot increase it, it's limited, it's the spectrum we have, but the number of antenna increases, the capacity increases, and then we have more cross-stream noise with MIMO, but the good thing is that noise goes to the logarithmic function. So we have the well-known MIMO gain, the MIMO gain. So this is, I think I give this example first, that there are 2 users simultaneously can transmit and receive from an access point which has more number of antennas. Then multi-user MIMO, similar to OSDMA, it has its own consideration. It has to be frequency, time, and power synchronized. And it's even more challenging because MIMO is more sensitive to these synchronization errors. So again, the use of trigger frame helps with this synchronization. And of course, with OSDM system, it has a cyclic prefix, and cyclic prefix is defined such that not only to take care of the delay spread of the channel, but also allows to, a jitter from these users, a little bit of, delay from users receive it. As far as they come within the CP, it is decodable. And also, once we have multi-user MIMO similar to FCMA, the collision reduces, the contention reduces, the whole overhead of going through this contention and reserving the channel for different user reduces. And same as OFCMA, I said before, now here is more even serious for the MIMO that AP needs to do phase-time frequency tracking. And AP needs to be really in control of the system, schedule users, group users together with more intelligence. So, what transmit patterns they need to use and so on. Okay, so this is slide I should have had it earlier. So in Wi-Fi, when they developed 11A, 11G to make it really simple device and easy for implementation, they had only 64.15 megahertz of bandwidth. So now, 10 years ago, or more than 10 years ago, 15 years ago, 17 years ago, when it was AG time frame, the 64.50 was something that Wi-Fi could do it and still maintain the cost. But nowadays, going through 256.50 or higher was doable. So they increased the number of the 50 points from 64 to 256. This way, the OFDM symbol became 4 times longer. So if you were transmitting one OFDM symbol in 4 microseconds, now one OFDM symbol is going to be transmitted in 16 microseconds. But the data rate shouldn't matter because now you have 256, you have 4 times more subcarriers to load this data. So, I mean, just from high-level point of view, the rate wouldn't change. But what will change is the CP or cyclic prefix or guard interval overhead. Because in 11A, G, and those things, the OFDM symbol was 4 microseconds, 0.8 microseconds, which was 1/5 of it, was the cyclic prefix. So really the OFDM at 64 point FFT at 20 megahertz sampling point was 3.2 microseconds. Then 1/4 of this 3.2 microseconds, which is 0.8 microseconds, was added as a cyclic prefix. So the CP overhead was 25%. Now the symbol is longer, the delay estimate is not longer, right? So we still need 0.8 microseconds of cyclic prefix, but now 0.8 microsecond is the overhead out of 16 microseconds. The symbol increased. So this way, effectively, it's more efficient because we have less overhead of cyclic prefix. So this was the task behind going the 256 point. To reduce the cyclic prefix and also to address the outdoor channel. Outdoor channel has longer delay spread, so it needed the longer CP. And in that way, we can service outdoor channel with using the longer CP, of course. And when you go to outdoor channel, the CP overhead is increased, but that's very dynamic. Whether you are indoor or outdoor, you can change the CP. Access point can change the CP. And the CP is actually signaled in the preamble of the packet, so it's completely dynamic. As the station receives the packet through the preamble, figures out what is the CP of the data portion and adjusts it accordingly. So this was the task behind going to 256 point FFC. It added some other efficiency here and there, like you have more subcarriers, so the number of subcarriers assigned as a guard band between channels or at the DC for DC cancellation is, you can have less number of those subcarriers. So that's the added efficiency. But then it doesn't come for free. It has its own complexity added. For example, now you have 256 subcarriers to figure out what is your channel estimate. So the channel estimation needs to be more, unless you do, skip some of the subcarriers and do the interpolation, which actually happens in Wi-Fi 2 in AX. And you have more number of FFC. This is 256 point FFC in 20 megahertz. In 80 megahertz, it's 1024 FFC. So the device has to process 1024 FFC, do the MBPC decoding, and let's say it has 2x2 MIMO antenna. All of this needs to be received, processed, decoded, and figure out whether it has to send an acknowledge back or not in 16 microseconds of this turnaround time. So these are new challenges for Wi-Fi devices. Improve outdoor operation. These are the CP or cyclic prefix overhead I was mentioning. VHT actually stands for 11AC, very high throughput. So in 11AC, for indoor use cases, they define a short CP, which is 0.4 microseconds. So these things are for AC defined for 0.4, but traditionally is 0.8 microseconds. Then high efficiency, which is stands for A11AX. So if you look at the standard, there was a question before I started that how can you get the standard? Once the standard, you can go to 802.11org, search for it in Google. It says all the contributions are there are public, but the standard drafts that are published amendments, I believe you need to be members of 802.11 to get access to it or purchase it. And then the one that is under development, such as AX, is not public. But you can look at the contributions, and in each meeting people go discuss, they have presentation, you can look at them. But usually it's, I think most of communication companies, they send people to a standardization meeting and they're members, so you can ask them to give you a draft. So anyway, that was a diversion from the discussion. But if you look at the standard, when you read the standard, it doesn't say AC or AX. The standard defines VHT station, which is very high throughput station for AC, or high efficiency station, which means that it's AX. Now, the AX guard intervals are 0.8 microseconds is the smallest one, so it's very low overhead of the CT, but it has also defined 1.6 and 3.2 microseconds. 3.2 microseconds is again 25% CP overhead, but it is used in outdoor channels. The 0.8 and 1.6 are used in indoor channels. The 1.6 microsecond is defined to be used with multi-user MIMO, uplink MU MIMO. So as I mentioned, this 1.6 microsecond is not only for taking care of the delay spread of the channel, but also the time differences between the users. So they're not exactly time synchronized. So it gives like extra 0.8 microsecond delta and offset between these users. 0.8 microsecond is for just indoor users. And then this is the LSIG stands for the legacy signal field. The one that I mentioned has a length field that AT uses to spoof of the legacy devices. Now in For outdoor, because the legacy preamble has limited range, how is it going to outdoor and operate once outdoor better? They decided to repeat this L6. So instead of having one OFDM symbol of signal field, there are two OFDM symbols of signal field. And the 11AX devices are aware of this, so they can combine these two symbols. So you see that 2 different times they combine them and they get 3 dB gain. And also other signal field of the preamble is repeated. Here is the high efficiency signal field is repeated that defines what is the rate and what is the cycle characteristics and what is the modulation scheme for 11AX devices. This also is repeated. And on top of all of this, dual carrier modulation has been defined. So it's like repeated in frequency domain. So again, they can combine it and gain another 3 dB to improve the outdoor operation as well as range extension. So X also extend range in downlink using this repetition and combining gain. And in the uplink, stations are going to use a smaller OFDMA allocation and concentrate their power in that smaller bandwidth to compensate for this power imbalance. The only thing to note is certain regulatory domains, such as in Europe, they don't allow 2 megahertz of bandwidth of operation. So the smallest operational OFDMA unit would be 4 megahertz. In US, 2 megahertz is allowed. So here's a summary of how it became more efficient. We are still in the same bandwidth and same frequency band, but we were supposed to improve the throughput by 4x, what the user throughput is, not really the highest rate. So in previous amendment, the target was from 64 QAM, they moved to 256 QAM to increase the pitch data rate. But here, the pitch data rate is also increased because we moved to have 1024 QAM. But in general, the main thing came from, more designing the system more efficiently. And one was that the subcarrier spacing became shorter. Instead of having 64 subcarriers in 20 megahertz, we have 256 subcarriers. Therefore, the subcarriers were not for the DC and on the band edges squeezed. So we have more number of subcarriers in general. Another important change was the time domain efficiency by reducing the overhead of guard interval or cycle characteristics. Again, because the number of the symbol duration increased or number of SSD point increased, it's called for its symbol, and finally the modulation is 1024 QAM, which gives better throughput. Now the timeline. So AX, a study group, started back in March 2013, and it was when the project authorization request document was submitted to IEEE standard board, and they approved it. So the study group formed. The study group studied the use cases and potential technology to be used. And once they see that, okay, it is feasible, actually I take it back, this study group developed PAR, and then PAR is approved, and the TG, the task group is initiated, and then they start writing the specification framework document which defines all the technology. And right now we are here actually The first draft was done back in November, and it was it received I think 7,000 comments to be resolved. So people are very busy resolving the comments till they get to the May meeting. Hopefully we get to draft 2.0. Draft 2.0 again will have thousands of comments until finalize. It's a very long process. But the good news is that once the draft 2.0 is ready, the WSA Wi-Fi Alliance, which commercialized the Wi-Fi brand, they work on certification programs. So you will see some Korea standard products. In fact, I think Qualcomm announced that they will have AX products by late 2017. And then at this draft, the main features are stabilized, so companies will have products, but the standardization effort continues, and they go through comments and comments resolution and over and the several drafts till finally they submit it to DevCom review committee of IEEE for final approval, and then the final standards will be published. And by this time, then it will be the base 2 certification of Wi-Fi Alliance that you buy devices which have brand Wi-Fi there that supports optional features as well. So in 2017, very unlikely that you see, like for example, 1024 QAM or even uplink multi-user MIMO may not be there. OSDMA will be there, multiplexing using frequency, but then by early 2019, then all the optional features will be there. So I think that's that's for 11AX. If there is a question.
Any questions about the talk so far? Or we can continue into the second part related to the low power wake up radio. Good. Oh, okay.
The AX is something.
Even if it's AP will do AX, you've got to have a mobile.
Oh, definitely, yeah.
Qualcomm's building the chips.
Yeah, they announced that they will have AX ready. So, but whether then it will be in your cell phone and laptops is another question. But you will see them. I think once this early product comes in 2018, the laptops and cell phone will then put them in.
But I guess my question, the heart of my question is, in an 802.11 AC environment, how well is AX going to work until there's the flushing out of the old AC?
Well, if access point supports both AC and AX, you should see the benefit of AX, because access point can reserve the media for AX devices and serve them in a more efficient way. So, and this is the basis of Wi-Fi. It's always backward compatible and coexists with legacy devices. It's just that I think a counterpart question to this would be whether the legacy devices will suffer as AX devices will pick up more and more. AC devices may suffer, and the main reason is for the special reuse and CCA. So Wi-Fi AX, the AC devices or Wi-Fi devices in general are very conservative. They look at -82 dB and they don't transmit. Now AX devices will be more aggressive. They will grab the media and transmit.
So in essence, you're saying the AX AP will clear the band for some period of time, and that should make everybody else be quiet. And even if there are only a handful of AX stations, they'll be able to take advantage of it and get better service.
Yeah, but it also depends on deployment and AP's scheduling algorithm. I think you don't want also to have your AC devices to suffer more, but in general, Wi-Fi is, the manufacturers tend to make more money, so they like to discourage people from using the previous, products, and be encouraged to buy new ones, right? Yeah, so that's the reality will happen.
So, can you talk about how does the new standard will evolve or will be part of the 5G? And then the other question is, in a special case, let's say in the high-speed chain, and then you have the latencies, then will that work for the latest AX standard?
Yeah, so the 5G question, .11 has started sending liaison to ITU meetings to be, to be involved in part of 5G efforts. Now, AX is not really going to be the 5G one, but once AX becomes, once some of these comments are resolved and the app becomes more stable, they will work on the new AX and the AX Plus. The AX Plus will target being part of 5G. But it still is not clear whether Wi-Fi will be a component of 5G or, like today's they are, offloading that carriers or service providers do from their cellular to Wi-Fi. It may continue that way as well. And the latency question, I think I didn't get it. So in the high-speed train, the access point is really servicing the train. Now, what is the latency between access point and, let's say, the satellite link it has? It's out of the scope of Wi-Fi. But once you are in the Wi-Fi system, the latency is handled through the access categories and quality of service defined in Wi-Fi. It shouldn't matter. Okay. So now on the 11BA. So this curve from ABI report shows the, how this wireless connectivity with IoT devices are going to be increased. And as you see in this curve, Bluetooth and 15.4 Zigbee are ahead of Wi-Fi. And as I said before, the real reason is power consumption. It's the real challenge for Wi-Fi to get into small battery-operated devices. Now, WFA has started efforts of defining certain features of Wi-Fi and a profile of Wi-Fi that allows lower power consumption. For example, we can define a subset of modulation and encoding schemes. Instead of supporting 64 QAM, we can support only up to 16 QAM, for example. And we can allow longer sleep period. Today, if your device goes to sleep for 1 hour, access point will be disassociated because access point expects that the device checks the beacon every 500 milliseconds or a second at most and the responses to the access point. If access point doesn't see any activity from their station, it assumes that their station has walked away and it's not in its range anymore and it clears up its queues. So now WFA is defining this profile to allow longer sleep period, a small, lower modulation coding scheme to allow better power consumption, but it still is not enough. And also, it's also latency is an issue. So if, let's say you have an IoT device, you want to have a temperature sensor. You want to, this temperature sensor is supposed to, read temperature and report back every hour. But if you want, right now you want to read the temperature, if the device is going to be in a sleep, then you have to wait because, we define the protocol that this temperature sensor can go back, can sleep, deep sleep for 1 hour is good. Power consumption reduces, but what happens, you have to wait till it wakes up. And after it wakes up, you can send a, command to it. So it's a problem of latency, right? Latency becomes the problem. So how can you address this reduced power consumption but also address the latency, not to wait long time? So this motivated the development of this receiver, low power wake-up receiver concept, which is the wake-up receiver is supposed to be it's supposed to be a companion radio to your main radio. This radio, its job, its function is just to receive a wake-up packet. The wake-up packet is a small packet, low throughput. It's just a signal, wake up. So it doesn't need to be, a QAM modulated signal. It doesn't need to be OFDMA, OFDM, this type of thing. It doesn't need to be MIMO. It can be a very simple radio, which with new advances in RFIC development, it can really consume like 100 microwatt active power. So 100 microwatt seems very aggressively low, but it has been researched in academia and the published papers that report that they have achieved this. And the way that they achieve this is that they use on-chip oscillator, like ring oscillator or LC oscillator. So those oscillators, as opposed to external crystal, consume really less power. So that the really power-hungry components of receivers are oscillator, is the LO and the PLL and the low-noise amplifier. So, but this wake-up receiver doesn't need any of them. Let's say you transmit in old-fashioned OOK on and off keying signal to it. So all it needs to do is energy detection, envelope detector, like old-fashioned radio. An envelope detector can detect that this is okay, this is a wake-up signal for me. And once it receives the wake-up signal, it can wakes up the main radio. Now, main radio is completely turned off here, unlike today's Wi-Fi, that the main radio is in deep sleep mode, but still it's not completely off because it has to maintain the synchronization. It has to know the clock that, okay, in a second later I have to listen to beacon, I have to wake up. But here it can completely go to a sleep mode, and then once it receives the wake-up signal, it turns on and can transmit. Now the standard is developing protocol. So what would be the, what is this packet format? What is the wake-up packet? Which actually, like in the January IEEE meeting, they sort of agreed that on-off keying is a good modulation scheme for it. And then now the protocol needs to be defined that, okay, if once this wake-up receiver receives this packet, besides defining this packet, then how would the .11 device wakes up, how would it respond? Would it send an acknowledgement back, for example, to access point that say, yes, I'm awake, send me the signal. So these are what is being developed. But the concept is simple. It's have a always on receiver which consumes really a small power, and it just always listens to receive this wake-up packet. And this wake-up packet can be transmitted as a actually I have some use cases here. So the wake-up packet can be transmitted as a unicast packet directed to certain address. Like here, between a smartphone and a smartwatch. Today, if you have Apple Watch and Apple phone, the Apple iPhone transmits through Bluetooth the wake-up. It's similar concept. It wakes up the Wi-Fi to Bluetooth, but not a dedicated wake-up receiver. And if you have a dedicated wake-up receiver which consumes 100 microwatts only, it will consume less power than even Bluetooth devices. So this can be one example of it. Another example is in a smart home that, for example, it can wake up to turn the light on, to bring the curtain up and down, and many other fancy applications nowadays with IoT devices. And it can also use with asset tracking. So if Wi-Fi is, battery, which doesn't need to be charged, then you can put on boxes and you can track them more intelligently than RFID tags. Another use case would be in sensor networks. Let's say you have many lights you want to turn on. You have many temperature sensors. You want to read their temperature. So in that case, you can transmit this wake-up packet. Can be a broadcast packet or multicast packet. So you can wake up several of these stations at the same time. So going back. So this packet can be multicast or unicast, but then there is also concern of coexistence. So this packet has to coexist with Wi-Fi. So access point has to contend for the media and then transmit this packet. This packet should be something that the Wi-Fi legacy devices or the non-wake-up receiver devices, even the, let's say, AX device, needs to be able to figure out that, okay, there is a Wi-Fi transmission going on and it has to, leave the channel, not contend for the channel during this transmission to avoid collision. So these are it's important to coexist with the current Wi-Fi devices, and as usual, very popular is to use the legacy preamble. Again, legacy preamble has the signal switch that it can be used to spoof off other devices. Or another method that is very popular for Wi-Fi is request to send and clear to send. So this is the request to send and clear to send is used for to avoid the blind spot and collision avoidance. So the device that wants to transmit something transmit request to send, and then access point sends back clear to send, and if this device is at the corner, other devices don't get its signal. The RTS, they don't get it, but all devices will hear AP, CTS, so they know that, okay, the media is reserved, the media is busy. So same thing can be used. So prior to transmission of this wake-up packet, access point can transmit and, can go through the sequence of RTS, CTS, and in this case, the access point can even send the CTS to self. It can send the CTS that is clear to send to itself and just get the media reserve and then transmit the wake-up packet. So these are the ideas that are being discussed and being standardized for transmission of this wake-up packet. But the real challenge is making this receiver to be really low power. Now, some people think that it is doable to build a receiver which is only 100 microwatts power consumption, active power, and it can be on all the time. Some people are in favor of duty cycling this wake-up receiver. So we can have a wake-up receiver that consumes 700 microwatts active power, but it can go to sleep and wake up, go to sleep and wake up. So that it has to have a better clock. So better clock means higher power consumption. That's why it moved from, instead of having 100 microwatts, always on power consumption, you can have 700 microwatts, but allow it to, go to sleep. And that way the average power consumption then is low again, 200 microwatts. So the main point is that this wake-up receiver has to give benefit over existing power save mode mechanism. The existing power save mode mechanism is that Wi-Fi device negotiated access point, how often it goes to sleep, and how, what's the periodicity that it wakes up from the sleep. So access point buffers the packets that are for the station. So let's say they negotiate ahead of time that every second the station will wake up and will listen to beacon. And inside the beacon, access point has a traffic identifier map that tells the station that station B, I have something buffered for you. So this time then it wakes up after 1 second and listens to beacon. It sees its ID in the traffic identifier map. It knows there is a packet for it. It doesn't go to sleep. It sends a poll to AP that, okay, I'm ready to receive this packet, and so on. So these are the existing power save mechanisms, and they are good. They are used today. The only problem is that the station needs to go back to wake up, go to sleep, wake up to go to sleep. These transitions are in fact really consume more power. And the idea of wake-up radio is that to avoid this transition and allow better power consumption. At the same time, it's always ready to receive the wake-up signal, so the latency is reduced. And this is the timeline for BA. So BA is a very new standard. It actually is a study group formed in July 2016, and it's the scope of the project, the purpose of the project, because it's a very small project and compared to like AX, for example, was approved in November, and the task group was formed in January. And it's going to be the specification framework document will be it's supposed to be done in 2017 and 2018. This is maybe quite aggressive and quite optimistic, but the idea is to have this, draft 1.0 ready by early 2018, and late 2018 the draft 2.0 will be ready. So hopefully once the second wave of AX devices or second release of AX devices are in the market, this BA can be aligned so they can have wake-up receiver with them as a companion radio. Anyway, as usual with that 11 standard, it goes through a long process of defining the protocol and drafting it, and then goes through the comment resolution to the final standardization. So I'm done.
You didn't mention anything about being able to address each wake-up receiver. Shouldn't there be something in the protocol other than that you're going to wake everybody up, which may or may not be important?
Yeah, good question, yes. So this wake-up packet, even though I made it simplified it by saying that it is only an envelope detector, but it actually carries some information. And the information bits are modulated like on and off ping, the information is very limited. So it has, it carries not really the MAC address, but like a station ID, something that during negotiation has been assigned, let's say 8 bits of information for the address. To address each particular receiver. Yeah, that's very good point that you don't want to wake up everybody, right? So because once this packet is received, it sends on the main radio. And another concern that people need to carefully address it is security. Because let's say if a hacker wants to come and drain all the batteries, all it needs is to transmit the broadcast wake-up packet and wake up everyone. So security needs to be addressed.
You used the example of sleeping or negotiating in 1 second sleep. I thought you could negotiate out to 100 seconds or 1,000 seconds.
Yeah, so these are 11V as a Victor. It's an amendment that allows longer sleep period. But it has not been really implemented because today's Wi-Fi is usually beacon interval is 100 milliseconds, and every 10 beacon interval, like a second is, usual like laptops and cell phones wake up. But yes, 11V defined longer period, it wasn't really implemented. So the way that there are, I showed certain amendments, but besides this amendment, that 11 has so many alphabets. It's a really alphabet soup from, B, AD, and all the, so we exhausted all the A's from AD to AX. Now it is BA. BA is a new one for this. And these amendments for roaming, for the network management, not all of them are implemented. Some of them are implemented through enterprises. Like 11V in particular is the one that WFA Wi-Fi Alliance is looking for to enable or implement some of its features for the IoT devices for low power consumption. Yeah, so it has a real-time clock, but it is not a very accurate one. So you can allow a lousy one which consumes less power, but it has an RTC. It has to have it.
As part of the
part of this receiver. So the receiver is a companion receiver, but the idea is that it will be integrated with Wi-Fi. So it uses, let's say, same antenna, for example. So it will be on one chip with Wi-Fi, but it uses, it doesn't use the external Keyless-Star. It has its own RTC, which is the PPM requirement, the accuracy requirement is much less than what Wi-Fi has.
So does the main access point log all wake-up packets so that if there are
spurious or illegal wake-up packets, it detects them?
That's a good question. I think that maybe people can look at it to see if there is any, anyone transmitting a wake-up packet that's not supposed to. But the idea is that the access point is supposed to transmit them. But perhaps as part of security solution, that's a good solution actually. That's a good prediction. I'm more focused on the physical layer and stuff, but I can tell my colleagues a real idea. So have someone actually monitors. That's what you're saying. Someone monitors the environment and see that, their wake-up packets are being transmitted that they're not supposed to, and do something about it.
You've mentioned that the AO2.11BA, one of the market it's trying to address is the one that's served by or dominated by ZigBee right now. But one feature of ZigBee is its mass network. It can multi-hop, which is more important in the industrial IoT area. Are there any plans for AO2.11BA to address that market?
So the idea of BA is really, even though we are talking about waking up to .11, but it can be used with ZigBee devices for asset tracking, for example, use case, which is mainly through ZigBee. These boxes can be equipped also with a wake-up receiver, and it's just, we don't have Wi-Fi, but just ZigBee, right? It can go with that too. Because what you're actually asking is, Wi-Fi has a mesh network. It's 11S actually, it's another alphabet for mesh network, but it's not implemented. And it's actually, the 11S is not very well defined. But so that's why the wake-up receiver, so today's Wi-Fi doesn't have mesh, so it doesn't make sense for wake-up receiver, which is companion of Wi-Fi, to have that capability, but it can be used with ZigBee. Also, there is some discussion on developing new waveform for Wi-Fi, which is low power. And in that discussion, there was, in fact, a study group looking at the low power, but it didn't get enough attention or enough votes. And the reason is that it's very tough if you want to go and be very low power and mesh or multi-op system, then ZigBee is there, right? I mean, going and competing with ZigBee, which is deployed today, so it's very difficult, right? But there are discussion of having new waveform for Wi-Fi for low power. And one way to enable when it is low power, especially on downlink, the transmit power is, the very easy way of doing low power is have limited transmit power on uplink. So the range is limited. The best way is to have mesh network, right? So extend it. So what I'm trying to say that the wake-up receiver, if there is a mesh, wake-up receiver still can be companion to that. It's transparent to the wake-up receiver operation. But today's Wi-Fi doesn't have mesh, or 11S is not deployed.
Can you talk about how does this low power standard compare with the Bluetooth Smart, which is also a very low power and for IoT application?
So Bluetooth, if you have, let me go back to this. So here, for example, Bluetooth is used. So so if between the cell phone and the watch, Bluetooth is used for a low power solution. But if you have a low power wake-up receiver at 100 microwatt, as opposed to 1 milliwatt that's Bluetooth hands. But of course, Bluetooth also goes through the power save cycle. There is you can show considering the cycle, the power save cycle of Bluetooth with 1 milliwatt versus 100 microwatt always on this backup receiver. You can see that the overall power consumption of this backup receiver will be smaller. In fact, there is a contribution. Maybe I have it in the references. Yeah. This contribution. Yeah. This contribution is Minion Park is my colleague, and I'm part of this contribution too. I'm an author of this too. So in this contribution, this is you can search for it and you can find it. It's in publicly available in 802.11. In here we have some simulation results, or some not simulation really, some analysis that compares Bluetooth with backup receiver and compares it with existing power saving modes of Wi-Fi, and it shows that using Wi-Fi, using this backup receiver can improve like 2x to 5x improvement in power consumption. It can give it. So that has more details. And now that I went there, I remember to actually acknowledge my colleagues. Robert Stacey is, I don't know if you have his book. He has written the Wi-Fi 11N, 11AC book. Actually, another colleague I had was Eldad Farahia. He left Intel. They wrote this book, and Dave is also a Zigbee person that had some of this ABI report information of the work that compares, Zigbee versus this Wi-Fi. Another question?
Simple question. How much the power for the normal Wi-Fi device compared to the wake-up?
Oh, today's Wi-Fi with OFCM are like 200 milliwatts. At the receiver, and yeah, it's much more. That's why you have the rechargeable devices. Yeah. Yeah, Wi-Fi is much more power consuming than Bluetooth.
Yeah, thanks for the talk. My question is, wake-up channel, is it going to be a TDM or FDM with the data, the existing Wi-Fi channels?
Yeah, so the idea is to make it simple. We are thinking to have this to be TDM. So it's content for the media and transmit one backup signal. But it is also possible for access point to transmit this backup signal, several of them in the multiple X-ray interfrequency domain. In fact, that reminded me a good point that I forgot to mention. This backup packet, so today Wi-Fi bandwidth is 20 megahertz, the minimum. But this backup packet doesn't need to be 20 megahertz. It can be as small as 4 megahertz, for example. It's just a backup signal. It doesn't need to be high throughput. It doesn't carry much of information. So if, let's say, if it is 4 megahertz and you have 80 megahertz of bandwidth or 20 megahertz of bandwidth, you can multiplex some of them. But it is challenging because when you put them in frequency, they cause adjacent interference to each other. And for adjacent interference, receiver has to have a good filtering, a blocker from adjacent interference. Anything you add here to do the better filtering, to remove the adjacent interference, it adds to the power consumption. So it needs to be carefully studied. So whether, if we put two of this backup packet in 20 megahertz, how much it potentially increases the power consumption versus the efficiency, it means that it is multiplex in frequency. But the idea is that these wake-up packets are not, you shouldn't see a lot of this transmission, because the idea is that these devices want to go to long sleep periods, and even if you have hundreds of them, but you transmit these things once an hour or less than once in 2 hours or something in hundreds of them. So it really doesn't take that much of time for TDM.
So I was listening to your talk and I was noticing that Wi-Fi seems to be extending into territories that used to be reserved for Bluetooth and Zigbee. So do you see Zigbee and Bluetooth disappearing in time?
No, and that was the reason that the study group that wanted to do a low-power Wi-Fi didn't survive, because the reality is entering this market and competing with these well-established devices is very difficult. But there is one thing, and it's the coexistence. So if you have Wi-Fi, you will benefit a lot from coexistence as opposed to, Bluetooth and Wi-Fi, because a lot of effort goes in for in-device coexistence mechanism between Bluetooth and Wi-Fi. Each of these devices have internal coexistence, right? That when, like for example, if Bluetooth is receiving, Wi-Fi doesn't transmit. So these things are handled in device, or it is, through the frequency hopping of Bluetooth. There are mechanisms for coexistence, but none of them are systematic and from network point of view. So if you have it from Wi-Fi, it's good. Another benefit is for manageability. So you have, let's say, in your gateway, you have Zigbee and Wi-Fi. You have two different software to configure them. If everything is Wi-Fi, you will have one software for configuration. So there are some benefits to have Wi-Fi, but it is, as we said, the Bluetooth and Zigbee are there to compete, and Bluetooth also is developed with WLAN. They are developing, better IP networks. They are developing, and then same as Zigbee, they are Bluetooth now is looking at Bluetooth long range, So it's like I don't think that it is something that you see Bluetooth and Zigbee disappear and Wi-Fi takes the place, but there is opportunity for Wi-Fi for certain IoT devices that require better, higher throughput, and they can afford higher power consumption.
Okay, thank you.
Stop at this point. Please join me in thanking Shahrnaz for our presentation and discussion. Finally, as a token of appreciation, we'd like to present Shahrnaz with a certificate of appreciation.
Thank you very much. I wanted you also to see this picture. Question regarding whether Bluetooth and Wi-Fi can be replaced by Wi-Fi or not. Bluetooth and Zigbee.